Good morning, everyone. Today we have Professor Rafael Piestun from University of Colorado Boulder. Professor Piestun received his PhD from Technion, and then he spent 2 years in Stanford University as a researcher, and then in 2001 he joined University of Colorado Boulder as a faculty both in Department of Electrical and Computer Engineering and Physics. Professor Piestun has received numerous awards and accolades, and he is currently a fellow of the Optical Society of America. He is also a director and the principal investigator of the NSF IGOT program on computational optical sensing and imaging at UC Boulder, and also a co-PI in the Strobe NSF Science and Technology Center. His research interests include computational imaging, sensing, super resolution microscopy, volume optics, and ultrafast optics. So please welcome Dr. Piestun.
Thank you for the introduction. It's a pleasure to be here when the sun came out. It's very nice here. Very interesting talks with the faculty in all the departments here. So today I'm going to talk about two topics that are somehow related due to the techniques we use. One is if this is the size of your spot of light, essentially the minimum spot that you can make with light, how to see objects that are 10 times smaller. Okay. And the other topic we are going to talk is how to image through an eggshell. Okay. So all these topics are within the domain of what we call computational optical imaging. And the idea is that if you are trying to get a generic image, you can use a lens as you have in your cellular phone. But to get more information from the systems, you normally need to use some other techniques. And the idea is that, for example, if you have an object here, you can use different types of illumination to encode information. You can use, for example, structural illumination, pulses of light, femtosecond pulses. You can use different coherence of light, coherent light, incoherent light, like you can use a laser or sunlight, etc. Then you can have optics that are more complicated than lenses. This could be, for example, grating, holograms, spatial light modulators, liquid crystal displays, etc. And then you have some detectors. Okay, so the detectors can be just one or could be several. And the idea is that you get information and you try to decode that information or invert the information. Essentially, try to recover information from the sample by using computation. The final image or measurement is what you like to have, and this not necessarily is an image, a nice image of that represents this. Could be some measurement of some property of the object. And here, this equation tries to summarize what the measurement is. So the idea is that the light is a multidimensional signal. If you are in engineering, you can think of light as a 7-dimensional signal. Sometimes simplify to 2 dimensions. For example, if you look at an image, it's a 2-dimensional signal. And then you have the response of the system to that signal. And that is what we call one measurement. Why go through all this when I can use just a lens? Well, the idea is that by doing this, you can encode information in a way that you retrieve more information from the sample, or maybe just the information you need from the sample, and actually capture information that is not there if you use just a lens. So examples are super resolution, compressive imaging, 3D imaging, getting all extended depth of field, pattern recognition, etc. So this is ultimately a philosophy of working in imaging, where you try to adapt the system to the task you're trying to perform. Okay, so the first topic is about diffraction, and I don't know if everybody knows what diffraction is, but essentially it's a wave phenomenon that happens when light, or a wave actually, crosses a sharp edge or an aperture. So here you have a a plane wave, and you see diffraction, essentially it's going to expand. It's also a manifestation of the uncertainty principle. If you try to focus the light tends to expand more in k-space. So if you have 2 point sources, like let's say you're trying to look at stars in the sky, you see 2 blurs, 2 blobs of light. And so if these become too close, at some point you cannot distinguish between the two, especially if you have noise in the system. And noise is always inherent to any measurement. So one thing you can think of is, I'll make these blobs smaller. Okay, so you can make them smaller by using a higher numerical aperture lens. That's what you do in microscopy. So you have a better lens, so you can make it smaller, but there's also a limit for that. The limit is essentially the wavelength divided by 2, about that, because the numerical aperture is about 1 at best. Numerical aperture represents the angles you can capture with the lens. Now, there's also a similar limitation in the third dimensions. If you're trying to separate point sources or emitters in the third dimension, and also depends on the wavelength of light and the numerical aperture. So this number for traditional, for visible light is about 200 nanometers. Here, this could be about 400 nanometers. And this is not new. These are the limitations of microscopy since the microscope was invented hundreds of years ago. Okay? So the theory of this resolution is also more than 100 years old, from Ernst Abbe and Lou Rayleigh. And what we are trying to do in this line of research that started about 10, 15 years ago is trying to get 1 order of magnitude better than the diffraction limit. Okay? So actually, the first proposal to do super resolution, essentially beat this diffraction limit, was proposed by none other than Lou Rayleigh himself. He proposed to use some types of phase mask to reduce the size of the spot size in spectroscopy. But for many years, these improvements have been incremental. So for example, confocal microscope improves over a wide field microscope by a small percentage of in the resolution. But here we're talking about 1 order of magnitude. And yeah, so that's happened actually in the last 10 years or so, and was the topic of the Nobel Prize in Chemistry in 2014. Hale, Morner, and Betsy got the Nobel Prize for fluorescence super resolution microscopy. So by using tricks, playing with the single molecules and switching of emitters, you can achieve the super resolution. So this is of interest in particular for biology because it opens a window that before was around 200 nanometers. Now you can go down to about 10 nanometers, maybe even beyond that. And so you can see things that were not possible before. So there's a big explosion of research in this area. And this is clearly a multidisciplinary area because it involves research both in the photophysics of the imaging, in the optics and signal processing, detectors, semiconductors. So a lot of things had to come into play to get this, to make this possible. This slide is a little bit dark in this display, but one of these techniques for beating the diffraction limit is based on the fact that you can, if you look at an image, you see normally with a regular microscope, you see a blurry image. But if you use the right fluorophores, okay, you can make only a few of the emitters emit at any given time. So you have a sparse array of emitters here, and you can localize each of these emitters with very high precision, much better than the diffraction limit. And then if you can switch to a different set of molecules, you get another localizations, and then you can build an image point by point. And I don't know if you can see it here, it's a representation. You can get a very fine image with high resolution. So for example, this is an experiment result. So here, this is what you see with a regular microscope and what you see with a super resolution. Okay? These techniques are known, and I like to call them localization-based super resolution, but there are different acronyms like PALM or STORM, and were first demonstrated in 2006. So some people think this is not an image because it's composed of points, but we know that that's already known that this is a painting, even though it's composed of points. And actually, I would argue that these images have more information because they have quantitative information about the localization of every molecule, and you can also get additional information about each molecule. So it's within the realm of what we call computational imaging, but also quantitative imaging. So the question is how to go from 2 dimensions to 3 dimensions. That's one of the contributions of my group. And for example, if you have because you're acquiring 2-dimensional images, so how to get 3-dimensional information. Now, if you think of an optical system, and the 3rd dimension means that the point emitters are going back and forth in the image plane. So if you just look at the blur, you could tell if this is in focus or out of focus. But for example, you cannot tell if it's behind the focus or in front of the focus because there is a symmetry there. So for once, you need to break the symmetry. And the other thing you can do is try to improve the sensitivity of the optical system to defocus. So one way of doing that is to introduce a phase mask in the what is called the Fourier plane, somewhere in between the lenses. And one example of a response you can get is two points that rotate. So as the object moves back and forth, the 2 point sources rotate. And so we call that the double helix point spread function. The point spread function is the response of the system to a point source. So what this allows is to, if you look at the orientation, you can tell the depth of the particle. Good. So because one image is worth 1,000 words, here you have this is a piece of glass where we made defects with a laser. And if you look with a regular microscope, you see the defects here. You can see this one is out of focus, but you cannot tell if these are in the same plane or not. If you go through the double helix point spread function system, you can see that here these have different orientations. And it's the same sample. So that means that it's more sensitive to distance than the regular lens. If you move the lens back and forth here, you get that. If you move the lens back and forth, you get that. So actually, these are rotating when you defocus. So how to establish this experimentally, which one is better than the other? So one way is to take, for example, 100 measurements and then look at the variance of the different measurements. So that's what you do. And then you can find the location and find error bars for this. So you take several measurements, calculate the 3D position in every case, and then look at the variance. And in this case, it was sub 10 nanometers, but it depends on the experiment number of, especially in terms of signal to noise. And we're going to see that in a moment. But the idea is that with a single image, you can get 3-dimensional information about the location of these particles. Now, this is experimentally, but clearly you need a metric that is independent of the particular experiment you perform. So in information theory and statistics, people use something called Kremers-Rao lower bound. This essentially tells you what is the variance of the error that you can get for independent of how you do the calculations. It's a fundamental limit, like the capacity of a communication channel is a fundamental limit. So this is a metric that allows you to compare systems. So essentially what you want is to have a lower variance or lower Kremers-Rao bound. And you can compare systems that generate 2 spots, systems that use an astigmatic lens, which is another trick you can do, put an astigmatic lens so the PSF looks like that in depth, or use 2 cameras or 2 images at different focal parameters. So this allows you to compare and actually to optimize. You can use this metric to optimize the mask that you're going to use in the system and the point spread function that you're going to use. Here is an example of how this is in tracking fluorescent particles. So here you can see the particles, but it's hard to tell the depth. Here, by looking at the orientation of the 2 lobes, you can tell the depth, so you can build a 3D map and track particles in 3D. Okay, so to do actually this single molecule localization microscopy experiments, it's the same way. You take a microscope, you need to switch molecules on and off stochastically. So for example, here you see 3 molecules emitting light. And what you're going to see is for each molecule, you see two lobes. And by looking at the orientation, you find the Z position. And then the central gives you the transverse position. You repeat this experiment, and then you build a 3D map of the location of the molecules. So one of the problems is that images don't look that nice. There is a lot of noise in these measurements, mostly because every molecule emits only a limited number of photons. So the images look something like this. You have a lot of background also from autofluorescence, for example, or autofocus emitters. So when you look at the image, you look at this. So you need to find the location of one molecule, and then from this image, estimate the location. So you can go and say, OK, the angle and the central give me the 3D position. But you can do something better, which is try to match this to a model of the system. So essentially, you have a very precise model of the point spread function of the system and try to match. And this is important, especially when you have aberrations, which is essentially deviations from the ideal response of the system. And you can actually measure that on the experiment itself. And here you see, for example, how aberrations can affect the point spread function. And so you measure this, and then you can interpolate between these by using something called phase retrieval, which is essentially wave propagation in between the planes where you measure. And this is important because we are dealing with with nanometric precision here. So the idea is that if you have this measurement, then you try to match to one of these images here, which is the point spread function in depth. And in order to do that, there are algorithms from the signal processing community and the statistics called maximum likelihood estimation. Essentially, the idea is that you're trying to maximize the matching between this and this, considering the noise statistics. So one thing that is interesting about these algorithms is that they are optimal. They actually can reach the fundamental limit of localization. Now, diffraction is not the limit now, okay? And that is because we are not dealing really with the linear optics. The limit of diffraction proposed by Rayleigh and Abbey is based on linear optics. Here we are having molecules switch on and off, so there is actually a prior knowledge of the sample because you know what you're looking at. And you're switching them on and off, so now the limit is not diffraction, it's actually determined by the localization precision. And localization precision is dependent on the number of photons detected. So it scales like the square root of the number of photons. So the more photons you have, the sigma, the uncertainty in the localization goes down as as 1 over square root of n. So that is your new limitation. There's also, you need enough sampling. Of course, you need enough fluorophores to sample. But this is a fundamental limit now. And of course, this is assuming you have a noise, what is called Poisson noise, which is determined by the quantum nature of the photons. There are isolated particles. And there are other technical sources of noise from the camera, the readout from the camera, background noise, etc. But experiments today in labs, you can achieve a 10 nanometer lateral resolution and 30, 40 nanometers axial resolution on a regular basis. So this is an image from a collaboration with W. Murner. These are bacteria. And what you can see here are different fluorophores with different colors. So you have 3 colors, essentially. And here, I don't know if you can see the squares. One square is 1 micron. So here you have 3D multicolor imaging. This is a live bacteria, but it's not moving. Let's put it that way. Okay. So one of the trade-offs is that you need to take multiple images to build one 3D image. So it takes some time. There are improved methods now that allow you to do this in a matter of a minute or so. But still, it's not real time. Good. So then there are other tricks you can play to get to beat the diffraction limit. So here we have, these are quantum dots, which is another type of emitter. These are they are brighter. And they are interesting objects to localize because they can also be used in biology. So if you look at this image here, we selected a blur where you can see that there is more than one emitter. So these emitters are about 20 nanometers in size. And you can tell there are several here, but you cannot tell how many. Okay? How many here think there are 3 here emitters? Any? Raise hands. How many emitters do I have here? 3, 4? Okay, maybe 2. So one way to trick this is to take a movie, because these emitters blink, okay? So these quantum dots blink. So now maybe you can tell better there is maybe 3 with the naked eye. So our brain is really good at this task. Actually, if you go to a party and you're talking to someone, even though there is a lot of noise, you can still understand what people are telling you. You can separate the signals in audio, and that's called a cocktail party effect. And actually, we use a similar technique here to separate these signals. So the assumption here is that each emitter is independent of the others, statistically independent. So then you can separate these signals by taking a time series. Essentially, you get a movie instead of and so in this special case, we found there are 5 emitters. Okay, nobody says 5. And this is very interesting because not only you can tell where they are, you can tell how many, you can tell where they are, and then you can also get the signal from each one of them. Okay, the time signal from each of the emitters. Now, in other situations, you don't have a time sequence, like in the case of localization microscopy, as seen before. So you might see something like this, and you know there's more than one, but you don't know how many or where they are. And this is important because we say we want to localize a few molecules, but we want to localize we would like to have more molecules on each frame so we can acquire the information faster. That's one of the current limitations. So to go from this to this, you need to be tolerant to having overlapping emitters and be able to separate them. Okay? So that is important, and there are several groups that have been working on this problem because it allows you to work faster in the acquisition. So here there is an example. For example, from this image, we can tell there are 2 emitters, and here we can tell there are 3 from this image. So we use some techniques that are borrowed from what is called compressive sensing, essentially trying to optimize it. So you use some type of optimization, trying to figure out where the emitters are here. And one of those techniques is called matching pursuit. You're trying to match the point spread function to these patterns that you acquire. And then there is some other techniques called convex optimization. And they are both good, and there are some trade-offs in terms of computation time and precision. So matching pursuit gives us some good localization, but convex optimization is much better. So we do a coarse, a fine tuning with different types of algorithms. So you can apply this by running a window through a big image and then get separate overlapping emitters. But in this case, I want to show the power of this. So this, if we look here, these are microtubules in a cell. And the color encoding tells you the third dimension. So here is a particular microtubule. And the average number of photons here per molecule was about 400 photons per molecule, which is pretty low. But if we take this microtubule, and because we have 3D information, we look at it from the front, then you can measure actually the radius, the diameter of this microtubule, okay, by averaging over this, just by looking at this piece of microtubule. And that radius is about 30 nanometers, which is consistent with what people have seen in electron microscopy and other types of measurements. OK, so just a warning, everything that I told you is wrong, almost wrong. I'm looking at the time here. Very good. So one problem is all what we did so far assumes that the molecules are isotropic emitters, are point sources. And that's not really true. Actually, molecules are better modeled like a dipole emitter. And a dipole emitter is not isotropic and has a radiation pattern, as you probably know. So that is a kind of a problem, right? Because instead of having a point spread function, what you have is a Green's function for the electrical engineers here. So essentially, what the Green's function it tells you is that you have a point spread function for every dipole orientation. Okay? Every direction of the dipole, you get a different image. So depending, you could get a spot, you get something like looks like a donut, or you can get something that looks like a peanut. And essentially, you have more dimensions, right? So you not only have x, y, z, you have also the two angular orientations. Now, not everything is wrong, because fortunately, these molecules are typically free to move around. So essentially, the dipole is free to explore the whole three-dimensional solid angle of orientations. And that happens very fast. So in the time of one frame of the camera, that molecule essentially visited all the orientations. And when you average all that, the radiation pattern is exactly the same as a point source. And that's why this works. If for some reason the molecules are not free to move, then you are having some systematic errors. But that's not a big problem if you know how to correct that, okay? So the idea is that then you need to take into account this Green's function, this response based on the orientation, and not only calculate the x, y, z, but also calculate the orientation. Okay, so you have a fine-dimensional imaging problem. So now you can also improve the system now in the philosophy of computational imaging by modifying the system to get more sensitivity to orientation. So here we use a phase mask and a beam splitter, a polarizing beam splitter, essentially separated two polarizations. And then you can have different patterns for every polarization and every orientation, and with that, calculate the specific orientation. So these plots are a little bit complicated, but what they show is that here we have the variance, standard deviation for 3D localization in blue, if you just take one image. And in green, if you take two images with different polarizations. And here, what this tells you is that by modifying the system, you can get more than an order of magnitude, sometimes 2 orders of magnitude better sensitivity to the position if you are looking at the dipole. Okay? So on this side, we have the same, but for the solid angle. So this tells you the sensitivity or the best precision you can get to the angle estimation if you use one image is in blue, and if you get two images with different focal settings, it's called bifocal, then you can also get at least an order of magnitude better precision. Okay, so the message here is that by designing the optical system, you can improve the sensitivity of the system and the precision to both the localization and the angle estimation for dipole emitters. And if you have if your molecules are fixed now, you can calculate both. And in a different collaboration with Mörner also, we did exactly that using the double helix point spread function and polarization measurements to find not only the location of molecules, but also the orientation. OK, so now I'm going to switch to the other topic. This a little bit expresses our philosophy of using computational imaging to tackle challenging problems. Here, beating the resolution limit was a significant achievement. We are tackling now here another problem which is very important, which is imaging through scattering media. So a typical scatter is the eggshell. The eggshell is very, as you probably can see, you cannot see through, but there's little absorption. It's mostly scattering, meaning that the light goes multiple paths inside this eggshell. So there was a paper a few years ago that actually brought this topic back to the forefront, because if you're trying to image, say, if you send laser light through the eggshell, say here this is scatter, you see a speckle. I don't know if you can see it here. You see a speckle pattern. Similar to the speckle pattern you see from a laser on the wall. Now, if you think of this light as a set of modes of light, okay, each speckle here is a result of the interference of several modes of light that go through this scatterer. So here you can write an equation, which each mode is this is coherent light, so it's expressed as a phasor. It's a complex number. So each mode is a phasor here, and they all add to one value here. And if these are random, then you get random speckle, okay, because these are random interference pattern. Now, if you can control these modes, the phase, so all these vectors more or less align, like in this case, you can get a much longer sum, complex sum, and then you get a focal spot. Okay, so if you can control the modes here by playing with the phases, you can focus light on the other side of the eggshell. Now, if you can focus light, then you can do a lot of other things. You can make multiple spots and things like that. So this one way of looking at this is thinking of the eggshell or the scatter, whatever it is. Could be skin, or could be any other object. You can think of an optical element. So ultimately, it's random, but it's one realization of a random process. As far as it's not changing, you can express it as using the scattering matrix, which is essentially a relationship between the input-output modes. So you have an input mode, you can measure what you get at the output. And if you come from the other side, you might get something different here. And you build this as a matrix. So if you go only from one side, you get this T, which is called a transmission matrix. Essentially, it relates what happens at the output when you come from this side. So this is used in electrical engineering all over, right? In networks, communications, circuits, and so on. So essentially, we're looking at the eggshell or the scatter as an optical element, and you can totally characterize this. So one way of focusing light is to say, OK, I know this matrix. I can calculate what is the optimum input, so I get a focus in a given spot. So that's one approach. Another approach is to say, OK, I'm going to control the modes and optimize and try to get the brightest spot in this location. And for that, use something called genetic algorithms, which is a way of optimizing the system. Use a special light modulator, essentially an array of elements that control the phase. And put a camera or a sensor on the other side to optimize the focal spot in that place. So genetic algorithm uses concepts of evolution, essentially trying to keep a population of vectors that is optimal in some sense, and then combining them and mutating them. So here we have what happens here. So the experiment is more or less like this. It's actually an eggshell. We have a camera on this side to see what's going on and provide feedback. Here we have the spatial light modulator, so the light goes through the eggshell. This is what we project on the spatial light modulator when we do genetic algorithms. So it's matrices that look random. And here, this is what you see in the camera, and this is the intensity at the focal spot here. You see it's increasing as we run the optimization. Here we do pixel-to-pixel optimization, so it's also increasing but slower. And here we do the transmission matrix. Essentially, we measure the transmission matrix, so there's no, until we measure all the elements of the transmission matrix, we don't have a focal spot. But then when we finish, we have a focal spot. But then we don't improve anymore. This one keeps improving. So this one is kind of slower, this is faster, but this one gives you an optimum focus. So there are different tricks to play around to modulate the light and get a focal spot behind the eggshell. So if you can make a focal spot, you can also write something on the other side. You can also make multicolor images on the other side. So this is projecting laser light through an eggshell. You get, with 2 colors, you can build an image. But the ultimate application is to apply this in biomedical imaging through skin, for example. And the problem is that the skin is moving, is not stationary, and things are changing in the order of milliseconds. So if you compensate for the scattering at one moment, a few milliseconds later, it's not good anymore. So one thing you need is to do it to modulate the light very fast. So we use the DLP, which is a MEMS, microelectromechanical system, essentially from Texas Instruments, that has very small mirrors that flip very fast at 30 kilohertz. So that gives us the fastest modulation you can get today with current technology. And we actually write holograms there. So instead of projecting functions, these are called Hadamard functions, we write holograms of the Hadamard functions, and we project those. And with that, we can do very fast modulation and updating. So this movie shows, this is a phantom, essentially a medium that is changing, and we continuously measure and focus, measure and focus. Okay, so you can see it's focused, then the medium changes, so we measure again, characterize the medium, focus again. And this happens in tens of milliseconds, so it's reaching the specs required for biological imaging. So this is in slow motion now, so the speckle disappears, and let's run it again. So you see, this is more in real time. Of course, the camera cannot, the frame rate of the camera is lower than the time, our measuring system. But it shows that the speckle disappears, but we can measure it again and recalculate the projection matrix to focus the light.
What is the target medium?
The medium is a gelatin that is changing, yeah. But so one of the problems in this experiment is that we were measuring behind the scatterer, and that's a little bit like cheating, because normally if you're looking in tissue or other applications in materials, you don't have access to the other side. So one trick is to use, as a feedback, to use the photoacoustic effect. So here we have the laser going through the spatial light modulator, focused through the scatterer here. And the sample target is behind the scatter. And then we have an acoustic transducer. When light is absorbed where a pulse of light is absorbed, there is an expansion, there is and then it's a generation of an acoustic wave in the several megahertz range. So we can detect that acoustic wave. And that allows you to do it on the other side of the scatterer. And we can optimize using the genetic algorithm in the similar way we did before, so you can increase the spot without actually seeing, without putting a camera behind the scatter. And then we find a way of, one problem is that the spot of the acoustic transducer is much bigger than the spot of light, which is a speckle size. So ideally, you want to get a smaller spot. And using this genetic algorithm, we found out that we can actually get a spot of light smaller than the spot of the acoustic focus. And here is depicted as here, if this is your acoustic spot and these are your speckles, this feedback is going to enhance the central speckle. So you get a speckle that, only a single speckle that wins in this genetic algorithm. So if this is your acoustic spot, you can get a smaller spot of light. So you can focus beyond the resolution of the acoustic transducer by playing some tricks. So here, this is a B-wing we put behind the scatterer, and we can image. If we don't use this algorithm, we don't have enough signal. Using this optimization, we can image with a good resolution, similar to the resolution of a microscope, optical microscope. So this is a photoacoustic image. This is the image in a regular microscope. And you get because in acoustics, you can also get the time of arrival of the signal, so you can also get the third dimension for free, because you have these signals are of much lower frequency. So this is interesting towards imaging through an opaque object. Now, lately we've been applying these similar techniques to image through a single fiber. Single fiber actually is similar to a scatter in the sense that it can transmit multiple modes, but these modes get scrambled, and then you see a speckle pattern. So traditionally, if you try to do an endoscope, you use multiple fibers, and there is a great interest now for neuroscience to image the brain, is actually to do functional image of the brain. So the problem with these bundles of single mode fibers is that they are relatively thick, typically 1 millimeter. What we want to do is use only one fiber that can transmit multiple modes. And these fibers can be around 100 microns in diameter. So it's an order of magnitude thinner. So you produce much smaller damage in the brain if you want to do brain imaging. So the idea is that these modes get scrambled, but if you unscramble the modes, you can image. So this is a sample. This is looking with a regular microscope. If you look through the fiber and do nothing, this is what you get. You get speckle. So what we do is we focus through the fiber, and now we scan by changing the modes, we scan the spot on the distal tip of the fiber, on the side of the sample. So we scan the spot, and then we collect all the fluorescence. We use a fluorescence sample, and we collect all the fluorescence and build an image through the fiber. And so we can compare the two. Here is, again, this is a tissue, mouse brain tissue. And if you don't do anything, you get something like that. If you scan, you can get an image. So this has been, we are collaborating with a group at MIT, which and we have shown that you can do actual imaging inside the brain of a live mouse, and also functional imaging. Good. So to conclude, we show that you can essentially beat the resolution limit if you play the right tricks, if you essentially get away from the linear optics paradigm and use computation in conjunction with knowledge of the fluorescent emitters. And we also show that you can actually beat the scattering problems to image through a scatterer by controlling the modes of propagation through the scatterer. And actually, the photoacoustic effect allows you to use this feedback to optimize the system. All the work in my group was done by students and postdocs. The top names work mostly on the super resolution project, the bottom on the scattering projects. I would also like to thank our collaborators, De Luca, Murner, and Murray in the photoacoustic projects. I have to disclose, a few years ago, we started a company to commercialize some of these technologies, and now they are commercial, actually, which is really exciting. Shows that what we do in the lab has some interest outside the lab. And of course, the sources of funding for the research. Thank you for your attention.
It's open for question. So I have a question. So when you are doing the scanning with the multimode fiber, how much time does it actually take to scan?
So we can do 10 hertz.
10 hertz, okay.
Now the image is probably about 100 by 100 pixels. It's not a very high resolution, but it's the only way you can do this.
So 10 hertz is the whole image. It's not like between one point to the other point. You're saying that?
It's a scanning microscope.
Okay, okay, okay.
Another technique that I hope to patent on, where you illuminate with a thin cone of light, and you actually get an area disk pattern that's compressed down to about 2/3, but you get a lot higher peaks. But by selecting the right wavelengths going in and out, you can get the peaks and valleys to line up, so you can just get mostly just a major central peak. And there's basically no depth of focus on this. So you can basically pick a point out of three-dimensional space and scan it in 3D space and so on.
Yes. So was that a comment or a question?
Well, I was just commenting on that. Have you
Yes.
looked at doing anything like that?
Yes. So there are different types of illumination, and there are actually two ways you can interact in an imaging system. One is in the illumination. You can use different types of airy beams or bezel beams of that sort, and you can also use that in the passive side, on the camera side, and get an extended depth of field. That's typically known under wavefront coding. Essentially, you get a very extended depth of field that then requires deconvolution. So yes, there are different tricks you can play with the mask, both in the illumination and the detection side. Yes?
So thanks for a great talk. So in the second half of your talk, you talked about these methods that are sort of limited by the decorrelation time of the tissue or the fiber, because changes the transmission matrix. I was wondering if you could comment on when you're doing fluorescence microscopy, you're limited by photo bleaching and also photon counts. What are some ways that we can try to overcome those limits to speed up these processes? What are the bottlenecks and how do we overcome those?
So the question is if we can, when we use fluorescence in a scattering medium, we have a limited number of photons, and clearly that's part of the challenge, because one way is to irradiate with more power, but there is so much power you can have. There is active research in making probes that are brighter, but in a very highly scattering medium to do fluorescence is challenging precisely because of that, and that's why we are using photoacoustic effect as a contrast mechanism rather than fluorescence. Because fluorescence, yes, you can focus, excite, but then those little photons need to go through the scatterer, and it's very challenging. So the photoacoustic effect is based on the fact that the acoustic waves almost have no attenuation, almost no scattering at those frequencies with tissue, and so they are better equipped to propagate in tissue. So I don't have a great answer for that in terms of fluorescence. Yeah, it's challenging. But people have done in relatively weakly scattering tissue, 2 photons, 3 photon imaging that can extend the depth, the penetration. Any other question? Yeah, sure.
So these are like multiply scattering medium, right, the tissue. And
Yes.
you are kind of doing only kind of two-dimensional phase shift. So what is the limitation? Like, can you do like as many multiple scattering medium we have, you can get a transmission matrix? Is there like a correlation between pixel size?
Yes, so you can, it doesn't matter how thick the medium is or how scattered, you can always calculate the transmission matrix and characterize that. The problem is that when you make a focus here, there's not all the light goes through to that focus. The thicker the sample, you have less light in the focus relative to the whole background. So it's a signal to noise issue. And then the damage you can incur in the sample based on the power of your laser. So it's mostly about damage threshold and signal to noise, yeah. Assuming you can always build a faster modulator and a more powerful laser, ultimately the limitation is how much power you can irradiate on the sample. Yes?
Question regarding this echo noise you mentioned. So it's a result of interferences between the scattered light, right? So how repeatable is it in practice, like between several or among several acquisition?
In the scattering example?
Yeah. Is it possible?
Oh, you're talking with the fiber? Or with the eggshell? Well, they are similar effect. It depends on how fixed this sample is. So if the scatter is changing in tissue, it's normally milliseconds. With a fiber, it's a little bit different because you can try to keep it straight, and we actually found ways of making a fiber more robust to coupling between modes, which is what distorts the signal. So depends on the particular sample, I would say.
The sample should be totally static, right?
Yes, yes, yeah. But if you have a fast system, you can remeasure this matrix in a matter of few milliseconds. So that's kind of the time scale. Josh.
Great talk. I wonder if you can comment on the use of your innovative multimode fiber in comparison to a green lens endoscope approach.
Yeah, so that's a great question. You can also use a green lens. It's essentially a cylindrical lens with an index of a cylinder with an index of refraction that is more or less parabolic in the radial direction, and that actually acts like a lens. And that's the competing technology. They are still relatively big. So we are talking about around 500 microns versus 100 microns with the fiber. And they are rigid, so they are not flexible, so they might incur additional damage in tissue. But yeah, definitely that's the preferred technology used now in these experiments. But it still has problems, yes.
So if there's no more questions, let's thank Professor Piestun again.
Thank you.